Hello everybody, welcome to my lecture. In this lecture, we are going to discuss about sources of power dissipation. First of all, let us know what is power dissipation. Power dissipation is the wastage of power, is called as power dissipation. To understand what is power dissipation, we need to know first what is peak power and what is average power. If you see this slide here, in this diagram, you can consider this as highest power. See this waveform is having less height compared to this is having high height. So when you ask someone to show the peak, what he will show? He will show the highest point. So that is peak power. Average power is the power over a period of time is called as average power. To any circuit, if you give large power for a short duration of time, it may cause a damage. So you can give lower power, less power for a longer time, which will not cause any harm to the circuit. And coming to this energy, the area under this curve is called as energy. Normally, if you have seen your mobile batteries when you buy in online, it will be given as 6000 mAh, 4000 mAh. What is that mAh? mAh is milliamp hour. So every electronic circuit is considered consumption of energy, not consumption of power. So it is not power consumption, it is energy consumption. Over a period of time, how much energy it is consuming is called as energy consumption. And even that batteries also, mobile batteries also are measured in terms of energy, energy storage and energy consumption. So coming back to this our topic, peak power is the highest amount of power that is consumed at any time. If the peak power is large, it may melt the interconnections of the IC. That may cause damage in the circuit, permanent damage in the circuit. Average power means the mean amount of the power that is consumed over a period of time. That is average power. Now, when you talk about sources of power dissipations may happen in two ways. One is dynamic power dissipation, another one is static power dissipation. Dynamic power dissipation is the one which happens when the inputs are changing. When the input levels are changing from 1 to 0 and 0 to 1, then it is called as dynamic power dissipation. Whereas the static power dissipation is power consumed when the device is powered on and no signals are changing. It is something like keeping your mobile in standby mode. Like, consider, I'm just giving an example for your easy understanding. Your mobile, for example, if your mobile is in flight mode and it is on, that means it is not doing any operation. Then it is called as standing. Like that, when the device is powered on and no operation is taking place, then it is called as static power dissipation. When the device is working, that means inputs are taking transitions. If any power is consumed during that time, then it is called as dynamic power dissipation. We can have a even clear understanding of what is dynamic power dissipation and static in the preceding topics. Now, these are the various sources of power dissipation. The two major branches are, one is dynamic power dissipation, another one is static power dissipation. Here if you see these categories, first one is switching power dissipation, next one short circuit power dissipation, and next is glitching power dissipation. These three are the only dynamic power dissipations. Normally dynamic power dissipation is very little. So these three, switching power, short circuit and glitching power, are the three dynamic power dissipations. And coming to the static power dissipation, in the static power dissipation, subthreshold leakage, gate leakage, junction leakage are the three major categories of static power dissipation. One is subthreshold leakage, gate leakage, and junction leakage. In gate leakage, you can again have gate oxide tunneling and hard carrier injection. Gate oxide tunneling happens because of thin SiO2 or thin dielectric layer. If you use a thin dielectric layer, charge carriers will escape from the gate and enter into the channel. That is gate oxide tunneling through gate oxide. Hard carrier injection is because of the excessive electric field of the channel will attract charge carriers from the gate. So that is hard carrier injection. And coming to that junction leakage, in junction leakage, the source and drain diffusions form a junction with the substrate. If substrate is N-type silicon, then the drain and source diffusions are P-type. Then it is a PN junction diode. These reverse biased junctions will have a reverse leakage current, which is called as reverse biased junction leakage current. And another kind is band to band tunneling current. These two currents happen at the interface of junctions. Coming to the subthreshold leakage current, there are many subthreshold leakage current mechanisms called as drain induced barrier lowering, narrow bandwidth effect, body effect, temperature effect, channel length modulation, gate induced drain leakage, channel punch through effect. Just remember these titles. Whenever there is a need to explain this, we will definitely go through this. Now, let us go much deep into dynamic power dissipation. Dynamic power dissipation, as we have seen in this tree diagram categories, there are three. One is switching power dissipation, and short circuit power dissipation, and glitching power dissipation. The first one is switching power dissipation. Switching power is the power required to charge and discharge the output capacitance on a gate. Normally in VLSI and low power VLSI, any digital circuit, when you speak about its outputs, when the output is 1, we normally consider as load capacitor is charged. When the load capacitor is charged, we consider output has become 1. When the load capacitor is discharged to ground, then we consider that as output became low. Output becoming high is treated as charging the output load capacitor. If the output is becoming low, is treated as discharging the load capacitance. Now, the formula for calculating the switching power is P total switch is equal to P transition and load capacitance CL into VDD square into F. That is P total is equal to P transistor into CV square F. Transition power into load capacitance into supply VDD supply square into clock frequency plus sigma alpha I Ci and VDD into VDD minus VTH into F clock. This is the final formula for static power dissipation. Now let us check why is this how is this coming. Now you can see here in this slide, when the output is becoming 1, then what happened, this charging current is flowing from the pull-up network to the capacitor, making the capacitor voltage rising slowly from 0 to a peak point like this. Now as the output is becoming high because of through because of the current flowing through this circuit. This circuit is called as pull-up circuit or pull-up network. When consider capacitor holding a voltage of 5 volts, which is logic 1. Now it has to be made 0. You have to see that this network, pull down network, is providing a short circuit to the voltage which is available across the capacitor. Now, because of the combination of the inputs that you apply, this pull down network provides a short circuit to ground. Now all that current which is there in this capacitor will be flowing through this pull down network and making the capacitance voltage to 0. So these are the switching activities. That is, output is made high and low, which is called as switching. So during this switching, if any power dissipation is taking place, then it is called as switching power dissipation. Now the energy stored in the capacitor is E is equal to integral P of t dt, where P of t, P is equal to VI, VDD into I of t, instantaneous current, where I of t is again I is equal to C dB by dt, which is very familiar. I of t is equal to CL dV0 by dt. CL is load capacitance, dV0 is output voltage. Substituting this I of t and P of t in the above equation, energy equation, now the energy function has become EC is equal to integral 0 to VDD, VDD CL into I means, what is I? I is equal to dV0 by dt into dt. If you simplify that equation, what has become energy stored in a capacitor EC is equal to CV square. E is equal to CV square, load capacitance into supply voltage square. Now energy per transition is half CV square. That probability of transition is half, because only two signals 1 and 0 are there, two levels 1 and 0. The probability is 1 by 2. So probability of transition 1 by 2 into CV square means CL, load capacitance, into VDD square. Now this switching power P switch is equal to energy per transition into F, because as we have seen in the energy diagram in the previous lecture, energy is area under the curve. That means E is equal to P into T. Now if you want to have P, which will be E by T, 1 by T can be written, 1 by T can be written as F, 1 by 2 can be written as F. Let me erase this. 1 by T can be written as F. Now the power is energy per transition into frequency. Energy per transition is probability of transition into CL V square dd. So probability of transition into CL VDD square into F. Now switching power has become C switch, that CL I am writing it as C switch VDD square into F. This is switching power. Now the second concept of dynamic power dissipation is, after switching power, it is short circuit power. This short circuit power dissipation is the power dissipation taking place during the transition of the signal. When you change the input from 1 to 0 or from 0 to 1, what is happening? For a very short duration of time, both the devices, pull up device, which is PMOS transistor in this example, and the NMOS device, both devices will be on will be on, providing a direct path from the supply to the ground, providing a direct path from supply to the ground for a very short duration of time. So that is called as short circuit power dissipation. In CMOS, both PMOS and NMOS devices are used. NMOS devices start conducting above 1.5 volts and PMOS devices start conducting uh, from 0 to 3.5 volts they will conduct. That means the overlapping voltage of around 1.5 to 3.5, that is 2 volts, almost from 1.5 to 3.5, 2 volts. When the input takes transition from 5, it slowly falls to 4, then to 3.5. That time the short circuit will be established between supply and ground through PMOS and NMOS transistors. When it goes down 3.5, 3, then 2, 2.5, then 2, then 1.5, till 1.5 both the devices will be on, and the short circuit is continuously giving power dissipation. When the input falls below 1.5, the bottom pull down network will become open circuit, avoiding this short circuit, stopping this power dissipation to happen. Now that power, short circuit power, is written as P short circuit power, as T short circuit, that is time of this transition, T short circuit, and VI, VDD into I peak, time, power, and how many times that happens. This input transition from 1 to 0 or 0 to 1 happens how many times? That highest number of times that may take place is f clock, that means clock frequency. So this may be simplified and written in another device parameter terms like width of the device, length of the device, and thickness of oxide. All this if you write, that will become an equation like this, which is short circuit power dissipation. The third and the final type of dynamic power dissipation is glitching power. This glitching power is happening because of the delay, that is because of the path delay of various signals. See, in this example which we have taken, all the inputs are taking transition from 0 to 1. When the first input, let me take this marker, when the first input has took a transition from 0 to 1, that will be present because there is no delaying element in the path, so that directly appears to that final NAND gate, AND gate, whereas the second input has to travel through two gates. One is NOT gate, another one is NAND gate. Because of this NOT gate, from 0 to 1, the transition which is input has becoming 1 to 0 here. That transition should be multiplied should be manipulated with the another input which is coming to the NAND gate. Now this NAND gate is getting 0 and 1 in the initial condition. 0 and 1 is 1, output is 1, so output has become 1. After this, the inputs to this NAND gate are 1 and 0, 1 and 0, and this 1 and 0 is fine. Because of this delay, this input is coming a little delay. So during that time, again when both have took a transition, output should be 1. Because of this delay, for a very little duration, output has become 0. Now the output actually should be a straight line for this combination of inputs. Because of the delay produced by this NOT gate, there is a dip happening in the output. This will be applied here, which has caused this many transitions in the output. This will lead to a malfunctioning or error in a digital system. And error, along with the error, what is happening, the number of transistors that a digital circuit takes will cause what? Dynamic power dissipation, switching power dissipation. Now, what is the reason for this is glitching occurs because of the input signals to a particular logic block arrives at different times, causing the number of intermediate transitions to occur before the output of the system stabilizes. These unnecessary transitions cause a power dissipation, which is called as glitching power dissipation. Now, contribution of different power consumptions you can see here. Switching power contributes 80 to 90% of the total power dissipation, whereas leakage power contributes 10 to 30% of the total power consumption. Short circuit power, which is happening through PMOS to NMOS devices, is up to 5% only. Now the another side of this power consumption is, one is dynamic power consumption, another one is static power consumption. This static power consumption is because of the leakage currents. Now this is the MOS transistor structure. In this MOS transistor structure, if you see, this is drain source contact and this is drain contact, and this is the drain diffusion region, and this is source diffusion region, and this is this gray color one is a SiO2 gate dielectric, and this is gate metal. These three are the contacts. Now there are many currents which you can see: I1, I2, I3, I4, I5, and finally I6 should be, this is I7, and this is I6 and I7. These currents are the leakage currents of the reverse bias junctions. I1 is the reverse bias PN junction current. Reverse bias PN junction current is I1 and I2. Now this I1 and I2. After I1 and I2, I3 is band to band tunneling current. I1 is reverse bias PN junction leakage current, and I2 is band to band tunneling, from one band to other band tunneling current. I3 is subthreshold leakage current. This I3 is because of the subthreshold leakage, this current is happening, I3. Now I4 is gate oxide tunneling current, as I have told you, because of the thin or the poor gate dielectric, some current is getting leaked through this gate terminal to the channel. This current is called as gate oxide tunneling current. Next current is gate current due to hot carrier injection. This hot carrier injection is because of the high electric field that is available in the substrate, will attract forcibly will pull some of the charge carriers from this gate electrode to the channel, which is called as gate current due to hot carrier injection. Channel punch through is happening. This is channel punch through. Actually the currents charge carriers are expected to travel from drain terminal through channel to the source terminal, but what is happening, some charge carriers are taking another path, and these charge carriers are not traveling through the channel but through the substrate. These charge carriers are traveling and reaching the source terminal, which is called as channel punch through. And the last current is gate induced drain leakage current, because drain leakage current should happen here, but this current is happening here. That is why it is called as gate induced drain leakage current. These are the static power and different static power consumptions. I hope you understood what are the kinds of power consumptions and what is dynamic and what is static power consumption. Thank you very much.